able to move down through them there.
Okay, got you.
Welcome and thank you for standing by. At this time, all participants are in a listen-only mode. After the presentation, there will be a question-and-answer session. To ask a question at that time, you may press *1 on your touch-tone phone and record your name at the prompt. This conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the meeting over to Mr. David Lamb. Go ahead, sir. You may begin.
Oh, again, thank you. I appreciate everybody's patience with today's webinar. We've done 60 or 70 of these at least or more and have yet to have any technical issues such as we face today with a slow server. But we will endeavor to persevere, I guess. So anyway, I want to welcome you to this afternoon's presentation on nutrient management and no-till cropping systems, which I think is very timely with the upcoming planting season, and I trust that you all get a lot from Gene Hardee's presentation here in a second. But before we go into that, I just want to go through a few housekeeping chores, so to speak, and you should hopefully all be seeing a list of upcoming webinars that you need to hopefully mark your calendars and participate in future events. The next one coming up is Common Bees and Best Bee Plants for the East on April 25th. And then actually the next one's coming up is the organic, on April 10th is one on organic pasture management, which will feature Joe Klein with Organic Valley and our own Steve Woodruff, who's the agronomist and grazing specialist here at the Tech Center. In order to advance our technical capabilities and get the word out, we're moving into the world of Twitter. And if you're interested in participating, we're giving away a free copy of the Building Soils for Better Crops for the first 5 folks who sign up today on the US East National Technology Support Center Twitter site. And you can see the link there. You can do that while we're going through my information, but this is a bound copy of this excellent publication on how you can improve your soils, and every NRCS person should have a copy of this. We already have one question on how to get CCA credits, and this presentation is available. If you are a certified crop advisor, you need to download the form, which if you go up on the toolbar menu on the right side, you should see the second icon left of the word feedback. You should see what appears to be a stack of papers. If you click on that, you'll see 2 documents there. You'll see this form. You need to download it. Print your name, make sure you put your CCA number and sign it and get that back to Holly Kirkendall at the information provided below, and I will remind you of this at the end of the presentation. But we don't know your CCA number, so if you don't put it in there, you ain't getting any credits. How you want to ask a question? As the operator said, everybody's in mute mode, but during the presentation, if you want to ask a question of Gene, I'll serve as moderator. You can type it in. Again, you go to the top, the question and answer button there at the top, and you can type in your question, and when I get a break in action, so to speak, I'll let Gene respond to that appropriately. So, those taken care of, I want to introduce Gene Hardee, who's been the senior agronomist here at the Tech Center for many years and got a wealth of information, and I think Gene's going to share his experiences and knowledge in presentation entitled Nutrient Management and No-Till Cropping Systems. So with that, Gene, let me bring up your presentation. And before I turn it over to Gene, I apologize if these slides are loading slow on your computer. There's nothing we can do about that, but we can make sure that we'll be patient and just plug on there. So, okay. All right, Gene.
Good afternoon. In today's webinar, we will examine nutrient management under continuous no-till. We will look at a number of facets, including nutrient availability and soil loss, or loss pathways, rather, soil sampling and nutrient application, and companion practices and treatments to further mitigate potential for nutrient loss. Historically, crop yield has been the overwhelming consideration in nutrient management recommendations, but we're now looking at optimizing returns and environmental impacts. The 4 R's is a concept developed through a long history of cooperation between the fertilizer industry and the scientific community. The International Plant Nutrition Institute endorses and advocates the 4R strategy as an appropriate nutrient management strategy. And the NRCS Conservation Practice Standard for Nutrient Management defines nutrient management as managing the amount, source, placement, and timing of plant nutrients and soil amendments. So basically for NRCS, we are also endorsing the 4Rs as a strategy for nutrient management. The conventional or historic cropping systems have provided an abundant supply of food and fiber, but at a cost to the soil resource and the ecosystem. With today's knowledge of the soil ecosystem and the technology available, we can provide for more sustainable cropping systems. Many of the concerns, though, with conventional cropping systems also relate directly or indirectly to nutrient loss and the cost of nutrient additions. As we look at this list here of the concerns with conventional systems, we note that most of these have some impact, as I just stated, either indirectly or directly with nutrient management. There are 4 basic nutrient loss pathways, or pathways for which we can lose nutrients. These include surface runoff, volatilization, leaching, and denitrification. Of course, there are other ways for nutrients to leave the field, particularly with the harvest of the crop, but these are actually the 4 primary loss pathways. In the poem, The Road Not Taken, Robert Frost laments the lost opportunity with the road not taken. But in nutrient management, pathways taken often represent nutrient loss, and greatest efficiency is typically gained by minimizing the movement of nutrients along these pathways. In the loss and the surface runoff, of course, phosphorus may be lost in solution or attached to particulate matter. The loss with nitrogen may be through this means, or there may be nitrogen may be lost by surface runoff, or it may not be. Certainly with organic forms of nitrogen that are on the surface, this can be a primary loss pathway. However, with soluble nitrogen, typically the rainfall will infiltrate unless if the soil allows sufficient infiltration. Normally the soluble nitrogen will go into the soil with the water infiltrating into the soil and not be the loss pathway so far as surface runoff is not real high for soluble nitrogen generally. Of course, the greatest change in no-till fertilizer or nutrient management should be in the nitrogen management. As we look at this slide, we see that nutrient losses under annual crops may range between 10 and 40 pounds under high rainfall environments. Losses by ammonia volatilization from surface applied urea may range from 20 to 40%. And nutrient losses of nitrogen as nitrous oxide from denitrification may range from 2 to 8 pounds per acre in humid regions. However, there are also impacts on loss pathways for phosphorus, and these must also be considered. Let's look at the potential impacts of no-tillage cropping systems on losses through surface runoff and leaching. This slide has a number of pictures from a study that was undertaken by Dr. Charles Roskowski, who was an agronomist at North Carolina A&T University here in Greensboro, North Carolina. In this particular study, Dr. Roskowski was looking at the impact of cover and no-tillage on runoff and soil loss. And in this particular study, each of these plots was set up with a weir and for a sampling mechanism to measure the runoff and the sediment. But let's look at the focus on the pictures themselves. And this was following a rainfall event of 1.8 inches on the morning of June the 12th, 2006. But this kind of the nature of a picture is worth 1,000 words sometimes. But in this particular case, the pictures on the left are those for Situations with no cover, the two on the right are for situations with cover. Of course, the ones on the bottom are no tillage, and the ones on the top are ones are treatments which have tillage. But look at these slides, and you will note that the water standing, which is making its way off the field and runoff, and you'll note that the highest water that we see there is the top left, where there was disc with no cover, followed by the no tillage with no cover. And by the no cover, that's meaning no cover crop rather than meaning no surface cover on the field. Then actually the disc cover probably has the less runoff than the no tillage with no cover, but that's probably a short-term thing in terms of the growth period, growing season for the crops. But look at the no tillage with cover, and you'll note that there's essentially no water that you can see standing within the plots. So basically everything within those plots that have no tillage with cover is infiltrating into the ground. So the point to make from this particular slide is that if there's no runoff, then there's no loss of nutrients through this particular loss pathway or the surface runoff. So certainly this is keeping good cover on the land is very important in terms of providing the cover that is needed.
Yeah, Gene, let me interrupt you here a second. I'm getting several questions about the fact that you're not seeing the slides or they're not loading. Again, I apologize for being the server problem we have. This is being recorded, so the replay, as all of our webinars, is available off of the Science and Technology Training Library, and generally is up by the following Monday, or off of the East National Technology Support Center website. Either one of those will get you replays of this. So I think I'm just going to have Gene continue to plug along here. This is going to be recorded. I would encourage you to stay with us and listen to as much as you can. And again, I apologize for the poor quality that we're getting today. So, Gene.
Okay. In the next slide, this slide entitled Effective Tillage System on Annual Phosphorus Runoff. This is from a study that was done at Kansas State University. And in this particular study, there was a comparison of phosphorus runoff under chisel disc tillage system and the no-till tillage system. Also, there were split treatments that had both one with broadcast phosphorus fertilizers and another in which the phosphorus fertilizer was knifed in or injected into the surface. In this case, you will note that the sediment attached phosphorus from the no-till was much less than that from the chisel disc. The total phosphorus was much less from the no-till, but the soluble phosphorus from the no-till was somewhat higher, or was significantly higher than that from the chisel disc. Carrying this a point further, though, one thing from this particular study, they found that knifing into phosphorus reduced the phosphorus losses by about 1/2. There was also a study in Wisconsin by Bundy that showed similar results, and also research at the University of Maryland found the efficiency for surface supplied phosphorus under no tillage to be greater than conventional tillage. In a study at Iowa State University, taking this a step further, though, they found that they got these same differences in which they got more loss of soluble phosphorus by surface runoff, by that loss pathway, if the fertilizer was surface applied, than they did with conventional tillage till plots. But they found that difference was primarily the first few rains after the application, that they found that difference diminished throughout the season until finally they were the situation for no-till in terms of phosphorus loss of soluble phosphorus, and for the conventional till plots were essentially the same. In terms of leaching of nutrients, or looking at leaching for a moment as a loss pathway, characterize the primary nutrients in terms of their mobility. All of you are aware that nitrate nitrogen is very mobile, so it's subject to loss by leaching. Phosphorus is relatively immobile. However, it is subject to leaching through coarse texture soils and through preferential flow. particularly when soluble phosphorus levels in the soil are high. Potassium is between nitrogen and phosphorus in terms of mobility, but potassium will leach through coarse textures, but typically is deposited at the top of the subsurface clay layer.
We had a question come in about the phosphorus. Does the form and placement, how could you overcome that with the no-till system? Were studies such that they would just broadcast, or was it put side by side with with a planter? Excuse me.
In this particular study I cited earlier, there were treatments with phosphorus that was broadcast both for both tillage treatments, and also for both tillage treatments there was treatments in which the phosphorus was knifed in. I'm not sure I understand the whole question, David, or whether in terms of means of reducing the loss, we're looking at that particular point in time in terms of losses by surface flow. Certainly, reducing the loss by surface flow injection or banding would certainly be a way to minimize that loss. There are other ways to minimize the loss of phosphorus by polymer coating of the phosphorus, some new technologies that are becoming available that might also minimize some of the loss pathways. But the primary loss of phosphorus, the primary way of reducing the loss by for surface runoff would be to actually put the phosphorus into the ground through injection, or some of the other things providing cover, which we'll get to a little later. In terms of leaching, carrying on, in terms of contrasting between no-till and conventional, and there was a 1936 study. I know this goes back a long time, but still, in some cases, old research can still provide some valuable insights. But there was a 1936 study by Dr. R.E. Horton in which he proposed that cracks, earthworms, insects, and root hair perforations enhance infiltration. And the reason I'm going back to that particular study, that was one of the first studies that cited preferential flow as having a significant impact on movement of or loss of nutrients from the soil. Many scientists have concluded that there's greater potential for leaching of soluble nutrients in no-till due to higher moisture and also the paths of preferential flow. If we look at the bullets here on the slide, you'll note that several studies have found little difference in leaching of nitrate between no-tillage and conventional, but at the same time, other studies, particularly in more humid areas, have shown greater leaching potential in no-till soils due to preferential flow and increased soil moisture. The studies at the National Erosion Sedimentation Laboratory have found that no-till produce more macropore flow. So where does the preferential flow in the profile and the soil profile end? That is a good question. Well, it depends on the soil moisture, the soil type, and etc. The leaching through the preferential flow has become a special concern for fields with tile drainage. And research at the USDA ARS National Sedimentation Laboratory in Mississippi, it's been demonstrated that matrix flow contributes the majority of the water moving through tile drains. The next point, that preferential flow contributes disproportionate amounts of soluble nutrients to tile drains, and that no-till produce more macropore flow than tile drains. There's a 1990s research project in Norway that demonstrated significant potential for soil loss through the flow of macropores to tile drains. This was the first study I found that actually demonstrated significant soil loss of the actual soil particles themselves actually going into the tile drains and contributing to soil loss. But that would certainly depend on the soil type. But in this particular study, the slopes were relatively flat, but there was actually more soil loss actually moving through the tile lines than there was by overland flow. In a study in Cornell University, in comparison of soil columns from conventional and no-till soils, They looked at these columns and found that nearly the entire depth of the no-till column was short-circuited by preferential flow before the till column solute had passed through the mixed unstructured plow layer, whereas basically in the no-till field, the flow passed readily through the micropores in this study at Cornell, whereas in the conventional till, it was had to pass through the plow layer and slowly pass through the plow layer as a whole unit, as a uniform flow before it reached the micropores. In a study in Hancock, Indiana, this was a study by the U.S. Geological Survey. They found that 25% of the nitrogen and 1% of the phosphorus loss was through tile drains. They further found that no-tillage increased infiltration. They found that macropores and no-till typically were continuous to the surface or near the surface. Also, they found that preferential flow increased the loss of soluble chemicals through tile drains. And finally, they concluded that conservation practices to minimize surface runoff and erosion may not reduce the transport of soluble nutrients to tile drains. Basically, citing these particular studies to kind of lay the groundwork for some of the treatments that we will be looking at as we proceed on through the discussion. I know there's a lot of information that is kind of being thrown out, but there's also additional factors of the nutrient pool which may be impacted by no-tillage that we need to spend a few minutes looking at also, in addition to the loss pathways. These are the nutrient placement, the impacts on soil moisture and temperature, stratification, and also nutrient availability. First, in looking at nutrient placement, nutrient loss, particularly through volatilization and with surface runoff, is significantly reduced by placing the nutrients into the soil. Continuous no-tillage may inherently restrict the opportunity for placement of nutrients in the soil or mixing of the nutrients with the soil material, though. Maintenance of residue cover may limit opportunities for incorporation of nutrients and mixing of nutrients through the surface layer. You might need special equipment may be needed for injection and banding of nutrients. High residue cover can also contribute to increased volatilization of surface applied nitrogen. Surface broadcasting of fertilizers can increase the potential for loss with surface runoff. And finally, the differences in rooting patterns under continuous tillage or continuous no-tillage. Normally, within a conventional till system, you have a relatively few roots or a smaller percentage of the root system in the uppermost part of the surface as compared with no-tillage. With no-tillage, with real good cover, then the bulk of the rooting system tends to be close to the surface. Of course, you might still get deep rooting depth, but the proportions that's close to the surface differ typically between continuous no-till systems with good cover and conventional till systems. Just a few notes relating to soil moisture and temperature and the impacts of no-tillage on soil moisture and temperature. Surface cover affects both the soil temperature and the moisture content, which can affect plant growth and nutrient movement. Lower soil temperatures under no-tillage can slow root growth and microbial activity in the early spring due to cooler temperatures, but no-tillage can actually moderate the soil temperatures during the warmer parts of the summer, providing better conditions for nutrient uptake and plant growth. Also, increased infiltration and low evaporation can add soil moisture and increase the flow of nutrients through the soil. This particular slide here is from a study conducted by Shanholz and Lillard at Virginia Tech University. And this particular slide it demonstrates or provides a comparison of the available plant soil moisture under no-tillage conditions versus conventional till. The difference is not huge, but if you look at this particular graph, you'll note that for both the 0 to 6 inch layer and the 0 to 12, and when that's also increased to 0 to 18, in each case, the available soil moisture, accumulated plant available soil moisture, is actually higher, significantly higher for the no-tillage than for the conventional tillage system, which basically points out the increased moisture and the value of no-tillage in providing moisture for plant growth. This particular data here was actually on, I believe, the third year of the no-tillage system coming out of a sod crop, a pasture or hayland situation. But there were other years in the study which basically provided similar type results. No-tillage also can impact soil temperatures. For those of you, okay, we now have the slide here. Okay, in this particular slide, this was from a study. It was actually done in Brazil, but you'll note in this particular study the moderation of the soil temperature by the no-tillage treatment. You'll see the line with the lowest altitude curvature there is actually a no-till plot. And when you compare this to the conventional till and or the chisel plow, you'll note that there's significantly lower temperatures through the daytime portion that is given in the graph there than there is for with the no-till. There's significantly lower temperatures than there is for the other two treatments. Next, we have a picture that is actually from Stanley County, North Carolina. This particular picture, you will note, this picture was taken by Nathan Louder, or provided by Nathan Louder, the district conservationist in Stanley County, and this was taken on July the 13th, 2011. You will note in this slide two contrasting plantings of cotton. These are belonging to two different farmers. The one on the left was no-tilled into a cover crop mixture with rye cover crop along with a legume and the mixture. The one on the right was a conventional till situation that was turbo-tilled twice before the planting of the cotton. The cotton on the left was planted on May 18th of 2011, and the cotton on the right was planted on April the 21st of 2011. So the one on the left was essentially 3 weeks later than or maybe a little over 3 weeks later than the one on the right. In this particular situation, Nathan took the soil temperature on July the 13th, 2011, and he took it 1 inch below the soil surface. He took it at approximately 2 p.m., and the temperature was taken from the row middles. And he found that the soil temperature on the conventional till plots or field on the right was 104 degrees. The soil temperature on the field on the left was 85 degrees. That's nearly 20 degrees difference in soil temperature. So this demonstrates the value that no-tillage with a good cover can provide in providing a better environment for plant growth and the soil biota. Now, looking at the causes or soil stratification or nutrient stratification in soils and the causes of that stratification under continuous no-till, there's basically 4 reasons or 4 contributors to stratification under continuous no-till. First is immobility of lime and some nutrients such as phosphorus, limited soil mixing, acidification from surface application of urea and ammonium-based nitrogen fertilizers, and finally delivery of nutrients to the surface through the natural cycling of the nutrients, that is by plants with deep root systems pulling up nutrients from lower levels and depositing those nutrients in decaying residues on the surface of the soil. Basically, roots tend to grow towards area, the concentration of nutrients, and this is probably the reason that most studies have found that even where there was stratification of nutrients, that it didn't seem to impact yields, but because of the fact that we're getting a higher concentration of roots in the layers that actually had those higher concentration of nutrients.
Gene, we've got a question to come in here while you're pausing. It says, wants to know two things. Well, what role does organic matter play in a no-till cropping system related to nutrient management?
Well, there's several things that organic matter provides a better environment for plant growth and uptake of the nutrients, a better environment for the soil biota, but it also provides nutrient cycling. Basically, it provides a continuous release of nutrients for plant growth, both nitrogen and phosphorus as well as other nutrients, and we will be getting to some of those points in a little more detail as we go on a little bit later.
Okay, one other question related back to the study with the macropores and going to the tile line connection. Do you know if that study factored in roots? Were those done with living roots growing in the soil?
I don't think those particular studies were not done with cover crops. I do have some information later on in the presentation where we will be bringing in the impact of cover crops.
Okay, good.
This particular study, graph rather, chart on that you see is from some information by Douglas Beagle at Penn State University, and basically these particular graphs is just to demonstrate the studies and the fact that we do get some can get stratification of nutrients within the surface layer, and the particular graph that you see displayed, this is actually a contrast of the soil pH within no-till treatments versus conventional till treatments. And you'll notice on the conventional tillage that for each one of those split increments and the top 8 inches rather, the pH levels are essentially the same, but if you look at the no-till, you will note that levels on that the pH level on the surface, the 0 to 2 inch layer, is significantly below the rest of the surface profile or the surface layer there. So basically, we get stratification in terms. We generally get lower pHs in the surface layer due to the acidification from surface supplied nitrogen, and that's a major contributor to the lower pH on the surface and where you get in no-till situations if the nitrogen is surface applied. And the next graph, also from Douglas Beagle, this focuses on the impact on soil test phosphorus at the conventional till and no-till. And in the conventional till situation, you will note there is a spike in the phosphorus level under the conventional till. And that is actually from the placement of starter fertilizer, and that's still showing up in the results later in the season. But that's the only impact, other than that particular spike there due to the starter fertilizer. Throughout the 6-inch depth, the phosphorus levels are essentially the same. But if you notice in the no-till plots, there is difference. The surface layer, the 0 to 2 inch layer, has much higher concentration of phosphorus. Phosphorus is immobile, as we noted earlier in the presentation, or generally immobile. So you don't get much movement down into the profile with, or the movement is very slow with the phosphorus. So you get, if it's surface applied, then it tends to remain in the surface. Both phosphorus and potassium are relatively immobile, so they will move, but you have to get high levels incrementally as you get movement down of those particular nutrients generally. The next slide here shows another study by, that was conducted in Canada by Dr. Ivan O'Halloran. And in this particular study, you will see again that you have stratification of the nutrients in the no-till. You have a wide difference between the levels of phosphorus in the upper part of the surface versus the lower part of the surface. We'll note here that this particular graph is actually in centimeters, and I was just making that note to you as an explanation. Actually, the actual movement of phosphorus is, the decline is much more rapid in terms of depth than we might get the impression if you're thinking of that as being inches on your first glance there. One more study looking at stratification. In this particular study, this was a study from Purdue University, and in this study it looked at both phosphorus and also potassium, and looked at 3 different treatments: plow, chisel, and no-till treatments. And you will notice again that this study also showed stratification for the no-till. But one thing to note here is it also showed nearly close to the same stratification with chisel systems as it did with the no-till treatment. To eliminate that stratification would take a fair amount of mixing, such you would have in a turn plow situation, but certainly that would open up the soil to a lot of other concerns.
Yeah, Gene, we had a question come in related to the Beagle study, and they had a question that said that that it wasn't showing stratification with respect to depth, but it was showing changes in peat content with respect to distance from the crop row. And I could go back up to that. I don't know if they were just wondering if you had a comment on that. I think it was the bottom there.
Well, it does. It actually, if you look at the depths there and look at the line, these are the distances from the row middle. But if you look at the soil test level throughout the whole arrangement there from the row middle, you note that on the no-till, the concentration within the 0 to 2 inch depth is significantly higher than it is for the other increments. And if you look at the conventional till, the actual concentration of phosphorus is essentially the same throughout, other than this one spike there that is caused, I believe, David, I believe you're on the one for the pH there rather than the one for the phosphorus. Thank you. But the spike there in the top graph there for the conventional till is due to Dr. Beagle attributed that to being due to the area there close to the row where you had starter fertilizer. Everything else in the conventional has essentially the same concentration of phosphorus. If you look at there again at the no-till, you will note the higher concentration in the 0 to 2 inch depth than any of the other 2 inch increments. So.
One more question. I hate to bug you here, Gene. Another question says, why do all the studies assume surface application of nutrients in no-till? And I guess that's just the preferred method.
Well, that was the main. This was to look at these. If one of the ways of overcoming that is not to assume that there's going to be surface application, but it's just looking at what the problem would be with surface application. Of course, the best way to overcome the problem of stratification is to place the nutrients actually into the soil, and not only to overcome the problem of stratification, but also to overcome potential for loss of nutrients with surface runoff. The best way to handle that is to actually place the nutrients into the soil by injecting or banding the nutrients and subsurface bands.
One quick thing, Gene, and I hate Gene's being a real trooper. Let me interrupt him here. So, folks, I've gotten a couple more comments. One of the folks in this suggested if you're having trouble, you can print these Gene slides out just down in the right-hand corner. There's a printer. You can print the PDF, actually print them out, or you can save them to your hard drive. and review them that way. So you may try that if you're still having trouble. Again, just to remind folks, we're having issues with servers that are beyond the control of the 2 or 3 of us here in the little room we sit in Greensboro, North Carolina. So, Gene, I'm going to let you keep going there.
Okay. Continuing on in terms of these special factors or special influences, additional influences related to impacts of no tillage. Nutrient availability would be the next one, and just a few things we need to consider in terms of nutrient availability and the impacts of no-tillage cropping systems is the cation exchange capacity or influence on cation exchange capacity, the nutrient type and organic matter, including the type and soil biota, nutrient cycling, and not just nutrient cycling, but also the continuity of the release of nutrients, availability of micronutrients, and also the increased mycorrhizal population. As we look at these, of course, in regards to nutrient type, this is particularly about organisms decomposing organic material with a wide carbon-nitrogen ratio, and microorganisms can free up nitrogen from the soil as an energy source for decomposition of high carbon organic material. Stubble decomposition tends to tie up nitrogen, particularly in the early years of no-till, and after the early years, buildup of soil organic matter, application of nitrogen can likely be reduced. One thing I'd like to note there in terms of availability of micronutrients is that organic matter provides natural chelates that maintain micronutrients such as zinc, copper, and manganese, and in forms that the plant can use. And that's one thing we don't hear too often in terms of no tillage and its benefit in terms of the soil organic, its impact on soil organic matter, buildup of soil organic matter, is its impact on nutrients other than those primary nutrients. Continuing on and looking a moment at the cation exchange capacity and the impact on cation exchange capacity. This is a table, or I'm sure all of you have probably seen similar tables from a basic soils 101 course or some low-level soils course, but basically this table shows the cation exchange capacity of various types of clays and also humus. And you'll note that humus has the highest cation exchange capacity potential of anything listed there. So it does have a lot of value in adding to the nutrient holding capacity of soil. Of course, the cation exchange capacity of both humus as well as kaolinitic clays is pH dependent, meaning that to realize that cation exchange capacity, you generally have to have a pH of above 6 or somewhat close to 6.5. This particular slide here is related to nutrient type and nutrient cycling and the continuity of release. A lot of the soil analysis reports that you see now will have a parameter listed as the ENR, or the estimated nitrogen release. This is a credit for nitrogen release from the mineralization of soil organic matter. Basically, the estimated, as I said, this stands for estimated nitrogen release, and it's the nitrogen release by mineralization of nitrogen during the crop season, which is available for plant uptake. And the ENR should be taken into account as a nitrogen credit to the nutrient budget. For those of you in the northern part of the U.S., you probably have seen this output a good bit on soil analysis reports. For those in the southern U.S., you may not see this because the soil organic matter is so low in the southeastern U.S. or the southern U.S. that most of the times the labs don't really worry about this in their soil reports or the recommendations. They don't worry about that particular nitrogen credit. And this particular slide here, this is a slide that was from a article in the there again, going back in time somewhat, this was an article from the 1938 Yearbook of Agriculture. It was a study by Dr. William Albrecht, but still some good information. This particular study shows nitrate release on soils with continuous cropping to corn. And you'll note that this is a long-term study from 1920 through 1932, and note the declining release of nitrogen and also the timing of the release of the nitrogen as the years of conventional tillage went on. So basically, what Dr. Albrecht was showing in this particular study was that with the passage of time, the soil organic matter and the potential to release nitrates was being eliminated. And we have seen this impact basically with the declining organic matter in many soils in the country, in the Corn Belt and other areas, and also with the subsidence and a lot of organic soils such as the Everglades. There's lower potential for those soils to release nutrients, and because of a lot of decline in organic matter. So basically, even though the organic matter has the potential to release nutrients to provide for plant growth, it must, that organic matter must be maintained. The cropping system must be able to maintain that, or that credit that nitrogen and other nutrients that are being released through that decomposition or mineralization of that organic matter is going to cease. As for the estimated nitrogen release, basically that normally amounts to about 20 pounds of nitrogen for each % of soil organic matter. Actually, most of the labs use somewhere in the range of 15 to 25%, depending on the region. And as for actually what goes into that particular computation, if you look and follow on the slide, you'll notice as an example, a soil with 2.5% organic matter has an estimated nitrogen release of 50 pounds. That is the 20 pounds per % organic matter times 2.5 would give the 50. And as for what really goes into that, if you look at the acre fertilizer is about 2 million pounds, then 1% organic matter, soil organic matter would be about 20,000 pounds. If you assume an annual mineralization rate of soil organic matter is between 1 to 3%, adjusted for geographical regions and crops, and continued on, the estimated nitrogen release is based on the rule of thumb that soil organic matter contains around 5% nitrogen. Then you would have about 10 pounds to 30 pounds of nitrogen for each percentage in organic matter. So basically, the midpoint of that was the 20, which was used in the study. Actually, used in the credit that is given by labs. Actually, in terms of the annual mineralization of soil organic matter, it's listed here as being around 1 to 3%. That is actually for the areas that normally get this credit. As you move farther south, the mineralization, because the warmer soil temperatures, would be even higher than that, probably in the southern U.S. closer to 5%. Well, how do we build and maintain soil humus that has the potential for cycling these nutrients? Just a few comments here in relation to that. As Albrecht had demonstrated earlier, continuous cropping without additions of organic matter soon depletes the organic matter. So it's important that we have cropping systems with the potential to certainly maintain, but hopefully even build with the current status of soil organic matter, to build on the soil organic matter. Of course, organic matter is relatively stable in the soil. As we saw in the previous slide, in most areas of the U.S., about 1% is mineralized annually, but that can be even more than that. Another thing, soil disturbance significantly increases mineralization of humus. So under conventional tillage with a lot of soil disturbance, that mineralization could go quite high. Continuing on, it takes about 10 pounds of organic material to produce 1 pound of humus. A large quantity of biomass is needed to build soil organic matter. But approximately 65% of the carbon in organic matter is given off in carbon dioxide due to microbial respiration. The carbon-nitrogen ratio of humus is around 10 to 1. So it takes not only carbon, but also takes nitrogen in order to build soil organic matter. if there's not adequate nitrogen available, then even more beyond that 65% of the carbon will be released to the atmosphere. Note that the bodies of bacteria have a carbon-nitrogen ratio of around 4:1 to 10:1, so it does take a good bit of nitrogen for the soil biota to carry on the functions of decomposition of the matter, organic matter, to fix organic material rather, to fix soil organic matter. This particular slide shows is from some work by Dr. Raywile at the University of Maryland, and it shows the influence of predatory nematodes on nutrient cycling. One of the reasons I included this just to show the nutrient release and a healthy soil. We do get a lot of influence by the soil biota. The predatory nematodes are a good indicator of a healthy soil, in contrast to parasitic nematodes, of course. But a healthy soil does release a lot of nutrients, but it also has the ability to capture and cycle a lot of nutrients also. In terms of soil biota, we might mention here that the particular soil conditions has a lot of influence on the particular soil biota. A soil with a high pH, for instance, favors the bacteria, and a soil with low pH favors fungi. And one reason I mention that is that fungi, particularly mycorrhiza fungi, is very important to the crops, and in terms of helping assisting the crops basically as an extension of the root system and helping the crops to glean immobile nutrients such as phosphorus, which the root system might not be able to reach without that assistance from the mycorrhiza. Basically, the mycorrhiza gets sugars from the plant, and in turn, they provide nutrients that are difficult for the plant to reach. With considerations of some of these impacts on nutrient losses and nutrient availability by conservation, by no-tillage systems, let's look at some basic nutrient management guidelines in terms of what we would do, recommend for production of crops and no-till systems. First of all, we should as a starting point, we should sample the soils and make adjustments, and those immobile nutrients, that is, make adjustments in the soil pH and the levels of less mobile nutrients prior to implementation. The second thing, we should follow university recommendations on sampling of continuous and no-till soils, and a couple of points there. We should normally the recommendation is to split the sampling depth on soils that are continuously no-tilled, at least periodically. And the university guidelines on how that should be split differ from university to university. Some recommend a 0 to 2 and then the rest of the topsoil layer in the other increment. Some recommend an even split between the surface. So basically they do differ, but basically all the universities recommend some sort of split periodically in terms of the sampling, basically to assess stratification and to refine nutrient management strategies. And also, a number of universities also make a point to recommend that the sampling be adjusted to account for spatial variability, because if the nutrients are being injected in bands, then you still have the potential for spatial variability, and in order to compensate from that, most universities recommend that there be more subsampling in actually collecting a soil sample, or that there be separate samples taken for the row area where the nutrients would likely be injected versus the row middles. And finally, in terms of this particular slide and the recommendations, the last thing there is to develop a nutrient budget that credits all nutrient sources, and that should include the estimated nitrogen release, nitrogen from nitrogen fixation, manures, compost, and also fertilizers. In terms of nutrient adjustments, I also might note that we saw the stratification in pH in association with no tillage. You note that lime applications could be more frequent under no-till, but generally you would have lower applications than you would under a conventional till situation. Continuing on with the basic recommendations, basically the standard recommendation is to adjust nitrogen application rate and timing as needed to account for building of soil organic matter and type of nitrogen by soil microorganisms. As we discussed briefly earlier, that basically you might need more nitrogen as you go into a no-till system, but later on as the soil health improves and you get more release of nitrogen from organic matter, soil organic matter, then this should be able to lower that nitrogen application. Also, they might have to apply more nitrogen up front in terms of as before the crop is planted versus a lay-by or side dress application as compared to a conventional till situation. The next thing is to use starter fertilizers for early planted crops and for crops with inherently slow root development. Basically, the research has been pretty consistent in showing that the results from application of starter fertilizers are even greater with no tillage than it is with conventional tillage. And just a couple comments. Remember that nitrogen and potassium are salts, so you have to be careful about how close and how much of nitrogen or potassium fertilizers are placed in proximity to the germinating seedlings or the plant's root system. Normally, a 2x2 application is recommended for starter fertilizers, that is 2 inches away from the seed placement and 2 inches below, but that is not necessarily true for all crops. The next thing there is to use banding or injection for application of nutrients to minimize the potential loss and to improve nutrient use efficiency. In terms of injection, I pointed out throughout the presentation the concerns with leaching, and particularly in terms of leaching on tiled fields because of leaching to the level of the tiles to macropore or preferential flow and having a direct outlet out of the fields into waterways. It's important, some scientists make a point, it's important to avoid injection directly over the tile lines where possible, and also maybe adding some sort of wings to injectors to disrupt the macropores and help to seal off somewhat the direct flow into tile lines. That's good. Okay. There's also a number of companion practices or treatments that I will list here. These are not just limited to no tillage, but they are some things that could be used to reduce the loss of nutrients under no tillage. The first one listed is fertilizer additives. This would include urease inhibitors and also nitrogen stabilizers, or also there's some new technologies for phosphorus stabilization to stabilize soluble phosphorus fertilizers, which involve polymer coatings that slow down the release. The other companion practices that we have listed here is drainage water management, which basically includes inline water control structures, irrigation water management. The next one is bioreactors, which is basically a new technology involving inline treatments consisting of wood chips or other organic materials in the trenches, basically to create an area for denitrification. There is one concern with that, is that the denitrification can also release nitrous oxide, which is a greenhouse gas, so though we might be reducing the movement of nutrients into water bodies, we might also be increasing the release of greenhouse gas with the bioreactors. And last of the companion practices or treatments is filter strips or buffers. There's been a number of studies that have shown that those filter strips and riparian buffers can also provide value in reducing both total phosphorus and also soluble phosphorus. One thing to note on these, most of these are actually impact the loss from the field, but don't really directly influence the nitrogen or rather the nutrient utilization efficiency. Let's move to some management that goes beyond just no-till, and look at these strategies. These are management practices that have a lot of potential in actually reducing the nutrients from the nutrient loss from the field. These include adaptive nutrient management, on-farm trials, injection of animal manures, application of gypsum, and diversity in cropping systems. If we look at going back to adaptive nutrient management, the potential impact of organic matter of nitrogen availability is well documented, but there are limitations of the present soil test methods for phosphorus and sulfur in that they only measure soluble forms and do not properly account for the contribution from mineralization of the organic forms and management histories. There was some research done at Maryland a few years back that showed that approximately 40 pounds per acre of phosphorus on no-till corn is often equivalent to 80 to 120 pounds of phosphorus on conventional corn. Based on this particular study in Maryland, they have significantly reduced its soil test-based recommendations for no-till corn. Every university does not have this supporting data to adjust recommendations, so this is one area that on-farm trials could support adjustments on individual farms. Adaptive nutrient management is not for every farmer to take on, but certainly it is something that could be very helpful in increasing the nutrient utilization efficiency on the farms. The next thing is injection of animal manures. Of course, injection of animal manures can provide for better crop response, reduced volatilization, reduced loss of phosphorus, nitrogen, and fecal bacteria and surface runoff, and also reduced odor. Of course, this technology for injection of liquid manures and slurries has been available for a number of years. However, injection has potential to significantly reduce the loss of nutrients through surface runoff and volatilization. Thus, it's an important practice for management of nutrients in no-till cropping systems. There are some considerations with injection of animal manures, though. These include that surface residues or standing crops can be an obstacle. Next, we may create significant soil disturbance, such as the unit that we see in the slide here is creating significant soil disturbance. It may lead to surface runoff. Contaminants from injected manure are closer to tile drains, and also equipment availability. Equipment that is available commonly is limited to injections of liquids and slurries. But that's not, hopefully not just the case in the future. There is equipment being developed that facilitates the injection of poultry and other dry litter. There have been two parallel efforts by ARS, one at the Soil Dynamics Laboratory at Auburn University and another at the ARS Dale Bumpers Small Farms Research Center in Boonville, Arkansas. And you'll see the two prototypes at the top there that came out of this research effort. The Agricultural Research Service is applying for patents on these, and one company has applied for a license to commercialize it. There's a coalition of Agricultural Research Service and agricultural scientists that are working to promote this unit across 5 Chesapeake-based states, and the coalition is led by ARS scientist Peter Kleinman and research partners at Penn State and Virginia Tech. Also, the Sassafras River Association in Maryland has a custom prototype unit that they are making available for demonstrations in 2012, and I think there was also a custom prototype unit that was used for demonstrations and made available to producers within a CIG project area in Pennsylvania. In addition to these, there's also been a unit developed in Canada, which you see at the bottom, but I don't have a lot of information on this particular one, but it appears that it does create a fair amount of soil disturbance. The next technology that we'd like to look at is, briefly, is the application of gypsum, and I'll mention this because it is promoted by a number of scientists as a treatment that can have some impact on reducing the loss of nutrients under no-till situations. Gypsum has been is primarily used as a source of calcium and sulfur, but there are other potential benefits that's coming out of the research, particularly ARS research, and you see these listed here. There's a number of different benefits. I guess the degree of those benefits would be where a lot of people say, well, maybe the benefits aren't all that great. So, but there are some incremental benefits that are provided, including reduction of aluminum toxicity, type of soluble phosphorus, improved soil aggregation, increased infiltration, and reduced runoff and soil erosion. As for the availability, gypsum is a naturally occurring mineral, but most of the gypsum, and the reason it's really being pushed by certain people at this point in time, is because there is an increased availability of gypsum at this point in time as part of the treatment process to reduce emissions of sulfur into the atmosphere. A number of power plants have a large supply of gypsum as a byproduct, and also in some areas with a lot of construction, they have a lot of wallboard, or what may be called by some of you as sheetrock, which basically is gypsum is the primary material within that, and that is also being used as a byproduct for land application of gypsum. So that is a treatment that I did want to bring in that does have some values that are being proposed, recommended based as the basis for recommending it for inclusion in nutrient management under no-till situations. And finally, I want to look at actually managing the cropping system itself, building organic matter and sustainability in the cropping system. And you see the things listed here. There's 8 different components that I've listed here. We're actually within a single cropping system. You may not include all of these, but these 8 things: diversifying the crop rotation, minimizing soil disturbance and maintaining surface cover, maintaining live vegetative cover when growing conditions allow, plant cover crops at times when feasible in the rotation, use perennials as a base for a strong rotation, included deep-rooted species at least in alternating years, included grazing animals to add vigor to the rotation, and applying manures, compost, and other organic materials to supplement nutrients and stimulate soil biota. These are things that can be used to build soil organic matter and sustainability in the cropping system. If we look at the first graph here, this is from some information from the famed Mora plots at the University of Illinois. Basically, you'll see that the lowest soil organic matter, or the one that's depleting the soil organic the system is depleting the soil organic matter the most, is the continuous corn. The the rotations are having less of an impact on soil organic matter. There's a term, the rotation effect, that is being used to describe the observation that yields are usually 5 to 15% higher in crop rotations than for continuous monoculture. And this has been demonstrated in this same study at of the Mora plots, that the yields are higher, significantly higher in when you have crop rotations than you do when you have monocultures. It's also been demonstrated at a dozen or so other research studies that I was able to locate from the eastern United States. But basically, if we have higher yields, then we're returning higher biomass and increasing the soil organic matter. Also, a very important component of that, of the diverse cropping systems to enhance organic matter and stability in the cropping system is cover crops. And the cover crops alone, we could spend multiple webinars delving into cover crops, but I just want to point out those benefits that deal with are related to nutrient availability and or the utilization of those nutrients and reduction of the lost pathways. There are other benefits that are not included in this list that you see here, but this list: fixation of nitrogen, increase in soil organic matter, cycling nutrients, enhancing nutrient availability, stimulating soil bioactivity, increased infiltration, and reducing runoff, and also reducing soil compaction and rooting depth. Certainly these influence or can help to minimize the loss of nutrients and increase efficiency in nutrient utilization. And this particular graph that you see, this is from some research by Dr. Ray Weil at the University of Maryland, and basically it shows the accumulation of nitrogen in various cover crops. Note that the cover crops on the rye particularly has a significant capture of nitrogen, but not as high as the brassicas that you see on the left. And the big point on that is the brassicas have a lot of ability to capture nitrogen and store it not only in the plant, the above ground plant material, but also in the root system. Cover crops do have a significant ability to take up soil nitrate and cycle that nitrate and reduce the movement of nitrate by leaching from the fields. This is a study from Ohio State University, and you'll note here that where there was a cover crop of oilseed radishes, that the soil nitrate levels was only about a third of that where there was no cover. In this particular graph, you note that cover crops also have an influence on the solubility of nutrients within the soil. And in this particular thing, this is also information from Dr. Ray Weil, and he noted that brassicas appear to be particularly adept at solubilizing phosphorus. That's important to note because brassicas do not host mycorrhizas. So this may explain the development of these particular species to exude these compounds, that is organic acid exudates from the root that help to solubilize phosphorus. Through the development of those species, that since they do not have a relationship or an ability to host mycorrhiza, which would actually bring phosphorus to the root system, then this was another way that these species evolved in order for them to compensate for inadequate phosphorus, was actually by releasing those chemicals to help release or solubilize the phosphorus. In this particular study, go back to nitrogen for just a moment. This is a study by Dr. Tom Casper at the National Soil Tilth Lab, and you'll note here the comparison for a number of years between situations with the rye cover crop and the control, and you'll note the dramatic reduction in nitrate levels in drainage water for those fields or those treatments where there was a rye cover crop as compared with those where there was no cover crop. That is also supported in the research project that was done by Dr. Ray Weil at the University of Maryland. This particular study, he was looking at the ability of radishes to capture nitrogen in the fall, and you'll note that the treatments with the radishes, basically you don't see the bulge in the nitrate levels as we look down in the soil profile for year 2003 or year 2002, whereas in the control without the cover crop, you see these bulges, these elevated levels of nitrates in the soil. And finally, from Dr. Ray Weil, you see this particular slide here, which was from a chamber that they actually were growing canola in, and then followed this up with soybeans later. And you note the root that the slide on the right or left rather shows the canola root that was growing on May the 3rd, or the void left by the canola root, and then you'll see on July the 17th the soybean root in that same void. So basically, a lot of these brassicas are cover and rye cover crops. Some of these species have deep, extensive root systems, fairly extensive root systems for annuals at least, and they have the potential to put in some macropores, some large voids within the soil there, which allows the subsequent crop to actually develop a root system in. There has been some studies that have been demonstrated that cover crops have significant potential for reducing the movement of nitrates and other nutrients by macropore or preferential flow. Some scientists say that the water can still go down the side of these roots, but still the distance from the root or that void is much smaller if it's plugged with the root. So there is a strong probability that the ability of roots from the cover crop, looking kind of the inverse of this year, if the cover crop roots are actually plugging those pores that are left by the previous crop roots, then those roots have significant potential to take up those nutrients and also kind of plug those and slow down the loss of nutrients from a field in which cover crops are present. Roots tend to take the path of least resistance. Plant roots and existing macropores may also partially contribute to reduce leach in continuous no-till situations where cover crops are used. And cover crops can also cycle nutrients in solution and take up soil water that would otherwise transport nutrients. This is from a study that was done by Dr. David Wright at the University of Florida. And in this particular study, he had 2 years of Bahia grass, the first year which was harvested for hay, the second year was grazed, the third year he planted peanuts, and the fourth year was in cotton. This is a system that Dr. Wright has, along with his colleagues, have been promoting for use in the Southeast. There have been a few takers and farmers they've worked with in Florida, Georgia, and South Carolina, and maybe Alabama, I'm not sure. But look at the benefits of this rotation. You see it had a 50 to 100% increase in peanut yield, a 40 to 40-fold increase in crop roots to 5-foot depths, an increase in cotton yields, reduction in parasitic nematodes, reduced use of fungicides, nematicides, and herbicides, increase in soil organic matter, increase in water infiltration. And as for an economic model based on this project, they figured that they increased the net profit for a 200-acre farm from less than $10,000 per year to more than $40,000 with this particular system. There are two components I would like to focus on for just a moment from this particular study, and the first is the Bahia grass, and the second one is the cattle. Dr. Wright and his colleagues estimated, or based on their measurements or the root mass from the Bahia grass in this particular study, they estimated that the Bahia grass produced around 20 tons of roots. So that's producing a lot of organic matter, adding a lot of organic matter to the system. Well, that is particularly important, particularly with the mineralization rates down south. It could be important in adding, building soil organic matter in any area, but certainly down south with the rates of mineralization, that is very important to add that high rate of biomass to the cropping system. And the second thing is the cattle. Dr. Wright found that when they included cattle, they got significant peanut yields, increases in peanut yields versus where they hayed for both years. Of course, if they hayed for both years, then we were taking off more biomass and more nutrients, but one thing they figured that was adding to it was that increased the amount of available nutrients within the surface layer. But Also, the cattle do trample in some organic matter and also increase the buildup of the soil organic matter too. So they're a component. This has been found not only in this study, but also by work that's been in done in North Dakota and some other areas. And finally, in closing, open for any additional questions and comments, but I would like to say as a final word here in terms of the presentation, to encourage in looking at nutrient management and a no-till cropping situation, to manage the cropping system, not just the nutrients, but think beyond just the nutrients and manage the whole cropping system. And that way we can really get at increased nutrient utilization, providing for nutrient utilization efficiency, and also minimizing the loss through these loss pathways.
Okay. Thank you, Gene. That's an excellent presentation, and I believe the system started to work a little better towards the end. So we're open to some questions now. Operator, if we got a few folks who want to call in and open the lines up, can go that route. And in the meantime, I did have a couple comments or questions come in that were written in. This was kind of back to the use of manures and its impact or use on no-till. The question is there any issue related to food safety and animal manure injections? I guess the concern being it might leach down into the
well, there are issues with certain crops in particular. There's root crops in particular. There are limitations in terms of use of that of animal manures related to production of root crops. For most other crops, there would not be any actual limitations, but there could be, and those are some with certain crops where the animal manures could come in direct contact with a commodity that's been harvested. Those are already really taken into account in the EPA and the FDA regulations. I guess FDA would be part of that too. Actually, the regulations for use of animal manures already.
And the only comment I'd add on that is if someone is growing organic crops, they need to be very specific and follow the guidelines as far as what's in the National Organic Program rules and regulations. Second question, operator, do we have any call-in questions?
Thank you. We will now begin the question and answer session. If you'd like to ask a question from the phone lines, please press *1. Please unmute your phone and record your name clearly when prompted. Your name is required to introduce your question. To withdraw your request, you may press *2. And it'll be one moment for the first question, please.
Okay, and while we're waiting there, we got another question again about solid animal manures. It says, what suggestions might you have about management of solid animal manures and no-till, such as poultry litter and beef feedlot scrapings, in terms of timing and placement?
Could you read that? Make sure I get the full gist of that, Dave. Would you read that one more time?
Yeah,
sorry.
Okay, what suggestions do you have about management of solid animal manures in no-till systems, such as poultry litter and beef feedlot scrapings, in terms of timing and placement of these manures?
Well, timing and placement would be considerations in these because of the fact that if it's solid, with these solid waste, then there's going to be a delay in release of a lot of those nutrients because they're going to be in organic form, of course. So that would need to be taken into consideration, but you would not want to apply that. I always want to follow the application up with a live crop so that you could be cycling those nutrients, certainly. I mean, you don't want to have nutrients that are available for movement by these loss pathways regardless, so you don't want to apply in the fall or anything like that. There's one thing I did want to mention and mean to mention as we looked at the slide with the solid the waste application or the poultry litter application, I wanted to call attention to the fact that poultry litter often will have a fairly high salt index, so that is something you also want to take into consideration. The distance from the crop, that relates to the question that was just asked in terms of placement. You would not want to place the poultry litter too close to the crop, or you really want to analyze the potential for salt damage to the crop because of the salt index of the poultry litter.
Okay. Operator, do we have any questions?
Yes, we do have a question from Mark Scarpetti. Your line is open, sir.
Hey, Mark.
Hi, Gene. How you doing?
Fine. How are you, Mark?
Good. Hey, I know your thoughts on no-till are very positive, and the use of cover crops came through loud and clear. As you know, in Ohio, you know the soluble phosphorus problems that we're having, and it seems like time after time we get presentations from different university folks that are similar to a lot of the studies that you showed, where they compare no-till to conventional till. But the difference is the no-till is always surface-applied nutrients, and they're comparing that to, on the conventional till, to basically incorporated fertilizer. And so I think the driving force behind a lot of that is actually the surface application of the fertilizer in their data. If you're going to truly look at no-till, shouldn't the no-till the cropping system be separated out from the method of application of fertilizer? Shouldn't you keep those consistent in both? Shouldn't you keep the application of fertilizer consistent if you're really trying to compare no-till to conventional tillage?
It definitely should, Mark, and that's a good point. Otherwise, you're kind of comparing apples and oranges, and it's you have a lot of built-in error there if you don't separate out the tillage. And one of the study that I cited, that I believe it was from Kansas, the impression I had gotten in reading the article, and they left with the research article, was that the data that I displayed was actually for surface applied material, both in the case of the no-till plots as well as the till plots. They did have treatments, though, that were where it was knifed in as well as surface applied, and the ones where it was, as an additional thing in the study, regardless of where it was no-tilled or where it was conventional tilled, they found that they got at least a 50% reduction in loss of phosphorus and surface runoff if it was knifed in rather than just being surface applied. Another thing, Mark, that I think, the comment that I made regarding adaptive nutrient management, and that was basically the reduction in the recommended rates of phosphorus that they would now have had for no-till corn or continuous no-till. And today's discussion is of continuous no-till, not rotations where you have 1 year conventional, 1 year no-till. But in the situation in Maryland, they had significantly reduced their recommended rates of phosphorus for continuous no-till as compared with conventional till, and based on this study that was done there that showed that there was basically they didn't need the high applications of phosphorus in a continuous no-till situation because of the greater efficiency and greater utilization efficiency of the phosphorus. And that gets to the point, as I made in the presentation, I really think that, and we think of adaptive nutrient management as being related to nitrogen, but I think there is also some potential here in terms of phosphorus, particularly for a lot of farmers that are kind of will move to new technologies fairly quickly. I think there's a lot of potential for them to significantly cut their phosphorus levels, maybe with adaptive nutrient management on-farm trials, and adjust their phosphorus application rates accordingly. So.
Thanks, Gene.
Any more questions, operator?
I'm not showing any further questions from the phone lines.
Okay, we got one more question, and then I'm going to cut this off, Gene, because I know it's been we're way past time. But Question came in about in areas of the country where animal manures are available without capabilities to incorporate, are we losing a lot of nitrogen in the form of ammonia nitrate?
Yes, we are have that potential to have to lose a lot by volatilization. Yes, that depends on the particular manure as to how much of the nitrogen is in the ammonium component. So that varies from depending on the manure itself, but that is certainly a significant loss. One thing, and David, I would like to make a note that I know there was a lot of fairly detailed material here, so if there are any additional questions anybody has, if they would send those to you or whatever, we certainly provide responses to those later on.
Okay, Gene. Again, I appreciate your effort. A lot of time and effort went into that and a lot of knowledge. As a way of closing, I want to remind folks about 2 upcoming webinars in the month of April. The next one on April 10th, Tuesday. That's our first in the organic series, Understanding Organic Agriculture, Organic Pasture Management. Tuesday, April 10th at 3 to 4 o'clock. And then on April 25th, Common Bees and Best Bee Plants of the East with Dr. Nancy Adamson. I did have a question related to the book I mentioned to begin with. It was Building Better Soils for Better Crop Production. It's a SARE publication. You can get a copy of it off the internet. And one thing I failed to mention